this lecture we will discuss the separation actions. Now, so far we have discussed T1 spaces and T2 spaces. Now, let us recall them briefly here. So, we call a space X a T1 space if for any pair of points, say X and Y in X, there exist open neighborhoods, um, say U and V, such that X is in U but X is not in V, and Y is in V but Y is not in U. I mean, if we can separate these 2 points by open neighborhoods, so these open neighborhoods they may not be disjoint. So here, this is the open set U, this is the open set V, and U contains X but not Y, and V contains Y but not X. So then we have the T2 spaces. So we call X a T2 space, also called the Hausdorff space. Hausdorff spaces. So we call X a Hausdorff space if any pair of pointers, I mean distinct pointers X and Y in X, if they are separated by disjoint neighborhoods. So here in D1 spaces, these U and V, they need not be disjoint, but when we talk about T2 spaces, these uh, open neighborhoods, they must be disjoint. So um, if for any X and Y in X, where X is not equal to Y, there exists open neighborhoods, say U open and disjoint neighborhoods, say U and V, such that U contains X and V contains Y. So we call these spaces to be the Hausdorff spaces. Then we did a theorem um, which states that a topological space X is a T1 space if and only if every one point subset of X is closed. So this is in some sense the characterization of uh, T1 spaces. Sorry, T2, I mean T1 spaces. So X is T1, uh, X is T1 space if and only if one point sets in X are closed. Now let us define what do we mean by the regular and normal spaces. So we have the definition of a regular space. So let X be a topological space. So such that one point sets in X are closed. So here we are assuming that this X is a Hausdorff space. I mean the T1 space. So the one point sets are closed in X. So then X is said to be a regular space. Regular space. Mm. If for each pair of if for each pair if for each pair consisting of a point, say x in X, and a closed set, and a closed set. So for this pair, I mean the point X and a closed set, say B of X. So for this pair, I mean the point X and this closed set B, there must exist uh, disjoint open sets containing X and B respectively. So this closed set B is such that it does not contain X. So and a closed set B of X disjoint, I mean let us say that um, this B is a closed subset of X not containing X. There exists open sets, I mean in this joint open sets, say U and V, such that X is in U and B is contained inside V. So diagrammatically, this is the open set U which contains the point X, and this is the open set V which contains the closed set, say B. So if this is the situation, if we can do I mean if we can separate this pair always, then we call X to be a regular space. Similarly, we have the normal spaces. So let X be a topological space um, such that one point subsets in X are closed. Then X is said to be normal. Uh, if for each pair of closed sets A and B, if for each pair uh, A and B of disjoint closed sets, of disjoint closed sets of X, there exists open sets, disjoint open sets containing them. Respectively. So suppose we have the closed set, say this is the closed set A, and suppose we have the closed set, say B. So they are both subsets of X. So if they are disjoint, then we call X to be the regular space, I mean normal space. If we can separate these two sets by open set, say U and V, and these open sets must be disjoint. So one can note from the definition that every normal space is a regular space. So this is the remark: every normal space is a regular space. So this follows from the definition of regular and normal spaces. So because one can identify this point as a closed subset of X, because we are assuming in the hypothesis that the one point sets are closed sets. So then this uh, space is normal space is also uh, a regular space. Now one can note here we need to include the condition that the one point sets are closed as a part of the definition of regularity and normality. So this is in order for this to be the case. So if we consider a two-point space in the indiscrete topology satisfying the other parts of definitions of regularity and normality, even though this space is not a house drop space. So let us make another remark here. So we need to include the condition uh, that the one point sets in X are closed. So let us, before this, let us do one more remark. So let us call this remark second. So this is the remark first, and let us do one more remark. So one can note that a regular space is a house drop space. So a regular space is a house drop space. So this also follows from the definition of regular and house drop spaces, because we are assuming the one point sets are closed. So in house drop spaces, we can separate any two distinct points by disjoint neighborhoods. So if I look at those 2 points in a regular space, they can be identified as the closure sets. So then regular space says that you can separate a point and a closed set by the disjoint neighborhoods. So a regular space is a house drop space, and hence every normal space is also a house drop space, because every normal space is regular, and hence uh, every normal space is a house drop space. And finally, we have the third remark, which is about uh, this condition. Mm, I mean, one point status in X are closer, so we are assuming this in both definitions. So why do we need these conditions at the first place? So let us clarify this here in remark third. So let us write this down. So we need to include the condition that x has to x I mean that the one point sets in x are closed in the definition of regularity and normality. In the definitions of regularity and normality, because um, if we consider a 2 point space in discrete topology, then such a space satisfies the other parts of the definition of regularity and normality, even though it is not Hausdorff. So one can know this is not Hausdorff. So then such a space satisfies the other part parts of the definition of regularity and normality. I mean, this space satisfies this portion over here in this condition, and this space also satisfies this portion over here. So such a space satisfies both the conditions, but this space is not in Hausdorff space. But we say that every normal space is a Hausdorff space and every regular space is a Hausdorff space. That means such a space cannot be, I mean, normal, even regular. So even though uh, it is not Hausdorff. Now let us prove a short result regarding the regular spaces, which in some sense is the characterization of regular spaces. So we have the theorem. So let us consider a topological space X. So let X be a topological space such that one point sets in X uh, are closed. Then uh, X is regular if and only if uh, given a point X in X, mm, and a neighborhood U of X, and an open neighborhood U of X. There exists a neighborhood, I mean there exists an open neighborhood V of X such that the closure of V is contained inside U. Let us prove this result. So we assume that X is a regular space. So first assume that X is a regular space. Let X belongs to X, be a point, be any point, and let U be a neighborhood of X. So then we have to prove there is some neighborhood V of X whose closure is inside U. Now U is given to be open, then the complement of U is a closed set. So then let us call B to be U complement. So this is a closed set. So this is a closed set that does not contain X because X is inside U. So that does not contain X. So therefore, by hypothesis, there exists a disjoint open sets V and W containing X and B respectively. So then, by hypothesis, because we have assumed that the space X is regular, so then by hypothesis, there exists disjoint open sets, say V and W, such that X is inside V and B is contained in W. Now one can note that the closure of V intersection B is non-empty. So we have this case over here. Let us call this V and V contains the point X, and let us call this W, which contains the closed set B. So this is the W. So note that the closure of V intersection W, sorry, intersection B, so it is empty. For if so, if we take Y uh, to be an element of B, so if Y is an element of B, then W is a neighborhood of B and B. So then clearly uh, then clearly um, then clearly W is a neighborhood of Y, but this W is disjoint from V, so it cannot be uh, so in this so hence Y cannot be element of the closure of V since V intersection W is empty. So that means so hence so if this intersection over is empty, hence V closure is contained in the complement of B, which is U. So this proves uh, the condition over here. So hence we are done in this direction. Now let us prove the other direction. So conversely, let x belongs to x and b be a closed subset of x such that x is not inside b. So we have to prove this space x is regular. I mean, we have to prove there are open sets, say u and v, which contains x, and other contains w, and these two open sets has to be disjoint. So let u be the complement of b. So then clearly u is open in x, because this v is closed. So by hypothesis, since x is not in b, so x will lie in the complement of b, which is u. So x is inside u. I mean, u is a neighborhood of x. Then by hypothesis, there is some neighborhood v of x such that v closure is inside u. So then by hypothesis, there exists an open neighborhood v of x such that v closure is contained in u. So let us call this to be the space x. So this is x, and let us suppose this is the open set u here. So this is u here. That means this is the u complement, which is b. Now we have a point x inside u. So um, we proved there is some open set v in x, that is, so this is open, so this is open set v in x such that the closure of v is inside x. Now the closure of v will also contain its boundary. So this is the v closure. So v closure is inside u. So let w be the complement of the v closure. Then clearly w is an open set in x, because this v closure is closed, and and this w contains v, because if we look at the closure of if we look at the complement of v closure, then it has to be in this set. So obviously it contains b. So therefore, so this is an open set in x. Let us write one more thing over here. So then clearly w is an open set in x disjoint from v such that w contains b. Therefore, v and w are the disjoint open sets in x containing x and w, sorry, x and b respectively. X and b respectively. So this proves the theorem. Now, same result holds for the normal spaces. So let us write this down here. So let X be a topological space such that one points are open in X. Oh, sorry, closed in X. So let X be a topological space such that one point sets in X are closed in X, then X is normal if and only if given a closed set A, given a closed set A and an open set U, such that A is contained inside U, there exists an open set V, in X, such that this open set uh, V contains U such that the closure of V is inside U. So the statement of this result is same as the statement of the result for regular space, but in normal spaces we just replace this X with the closed set A. So the proof of this result is also similar. Uh, so one has to replace the point X by the set A throughout. So let us mention this here. So the proof follows from, I mean, the proof, mm, the proof, mm, so this proof uses exactly the same argument. One just need to replace the point X by the set A throughout. So the proof uses exactly the same argument. Uh, One just replaces the point X by the set A throughout. So this is left as an assignment for the papers.